measurements. So we started in with significant figures. We're just getting warmed up, so this will be the chapter for that. Now, we've talked about how to identify the number of significant figures in something. What is going to become more important now is once you've identified them, is how to use them in your calculations, because that's ultimately what's most important. So, let's consider this type of problem, multiplication and division with significant figures, if you run across this in your calculations. It's actually very easy to do. It's the simplest type of math we can do with sig figs. For example, look at this problem, okay? 5.02, how many significant figures? 3. 89,665, how many? 5. How many in 0.10? Good. 2. All right, so whenever you're multiplying and dividing with significant digits or significant figures, all you've got to do is do your multiplication, type it in your calculator. When you type it in, you're going to see this number, which does not reflect the true precision of your data, okay? It's just how your calculator would spit out this answer. When that comes out, what you've got to do is figure out how many significant figures you can express in your answer based upon the certainty that you've obtained from your data. It's real simple to do with multiplication and division. You look and see whichever one of them has the fewest number of significant figures, which would be this one, right? There are 2 there. That means whatever your answer is, you have to round it off to 2 significant figures. It's that easy. So that's why it's written as 45. 3, 5, 2, your answer has to have 2. You can only be certain as your least certain measurement. That's what this is basically saying. Okay, so consider this one. How many? 4. How many's here? Okay, so that means you have to take this number right here and go to 3 significant digits. So 0.96, you've got one more place to go, so you would round up, right? So you'd go to 0.966, hence that answer. All right. Sometimes this rounding may make you think a little bit. That was an easy example, okay? You all know this, I hope. I hope you know basic rounding. You know, if it's 5 or... It depends on if you took a... We offer a course here that's Chem 061. It's sort of a real basic chemistry course to get you warmed up. I don't know if any of you took that or not. I don't think it's not required for anything. It's required to get into Chem 105, but not for this class. Sometimes you'll learn different methods of when to round, like if the number's odd or if the number's even. That's just to do with anything that involves scientific measurement to sort of balance out all of your numbers. Anyway, it's not important. Stick with right here just normal rounding as you always would do. If it's 2.34, I told you to make it 2 places, you would round down because it's not 5 or above. Now that you already know. And the same thing with this one. You would round up. Okay. If I asked you to round this to 2 significant figures, that was easy, right? Realize that what that means is, not 2 decimal places, but 2 significant figures. That means when you're totally done with everything and you look at your final answer, you can only have 2 figures that are there in terms of what's significant. In this case, you can't say it's 2.35. It's got to be 2.3. You would round down to just those 2 places right there. All right, now look at this one. This is where it sort of gets a little bit tricky. Not bad, though. 234. If I wanted you to round that to 2 significant figures and just write it normally, realize where you would have to go with this. You would have to go either to 230 or 240. Those are your only 2 options in that case, because remember, I say try to avoid those because those are ambiguous numbers. You really want decimal points in there if you can. But if you don't and you just have this to work with, you would have to round that number to 230 because 230 actually has 2 significant figures. That 0 is not significant. It's an ambiguous type of situation. So the best way to do that then, of course, would be write it in scientific notation. It's more precise that way. Okay, if you take 237, that would round up to 240. Now, even if I had 237.5, and I told you to round that to 2 significant digits, that 0.5 doesn't even matter. Okay, it's not going to make any difference because you still only are limited to 2 significant digits, 2 significant figures. So you would have to actually round up to 240 in that case. And there's an example of that. The 2 significant digits, regardless of all this stuff that's here, notice how big of a difference that makes in what the measurement that you are reporting. Okay, that makes a huge difference in terms of the scientific data. One, actually means you've measured it out to 4 decimal places, and that's pretty precise. This one, notice that 230 is considerably off from what this number truly represents. And that is important because that's what you have to communicate whenever you're taking measurements and giving them to someone else. And people in the scientific community look at those numbers in that respect. They look at the degree of uncertainty expressed in the numbers that you give. And so what that means is if you write something down, you'll see this later on in some of the labs that we do. If you write this down, and one of the things that you write down is like you're measuring mass on an analytical balance, and you write down 1.299 as your mass. That's good. I mean, you've got 4 digits there, 4 significant digits. However, then if you take the temperature, and on your lab report, all you write down is 34 degrees instead of 34.0 or 34.00, notice what you've done to your total calculation. You've limited your total calculation because one of your things that you measured only had 2 significant figures in it. Okay? So try to get as many as you can under those circumstances. Okay. Now, in this case, we're dealing with decimals, so we don't have nice whole numbers that we could round with like we did last time. So here's just another example. Let's say we're multiplying and dividing. We just do regular order of operations. You know that if you multiply something and divide it, it's all strung out in one equation. You just go in order, right? You should have learned that in basic math. So in this case, we have these numbers as written up here. That has 3 significant, that has 2, that has 4, that has 2. That means whenever your final answer, whenever you're done, you have to have 2. You're limited to 2 in your final answer. This is what your calculator would show, so you would have to round accordingly. So that's all that is showing. Same thing down here. You've got 4, 3, and 6. You're limited to the 3. And you have to round at 3 significant digits. That's why this is 1.52 and not 1.51863. Some people will, if I mark this wrong, some people are going to say you're going to have written maybe 1.5 or 1.519. And if I mark that wrong, you're going to say to me, well, I don't understand. This is the same number. Every math class that I've worked with in the past have never counted off or anything like this. Why are you? Because this is an application of math to data collection. So we have to include this kind of stuff in what we're doing. Okay, now this is where it gets a little bit different. It's still not hard. Okay, you can certainly keep this straight in your head. Multiplication and division, easy to do. Just count whichever one has the fewest. Excuse me. Now, when we're dealing with addition and subtraction, let's consider this. What you want to do, instead of looking, and this is where it gets kind of tricky, instead of looking at the number of sig figs that are present, when you add and subtract things together, you are actually looking at the decimal places present, as opposed to the number of sig figs present. So notice here, the best thing to do would actually be, I don't know if there's a marker over there or not. Maybe I can write on here. The best thing to do when you're actually adding these things up, I don't think the notes show you this, so, would be take this 5.74, write this 0.823 right underneath it, like that. Then keep your decimals lined up, 2.6, this is hard to write on, 51, and then sort of set it up, that's a 2. Hard to write, I can't. You get the point. All right, so those things are all added together. Now, when you set it up like that, what you can start seeing is, assume that these were, tilt your head sideways, and pretend like these are all lined up, okay? You want to look at sort of how far over the number goes from the decimal point in all of these situations. So you'll notice like 5.74 has the fewest number of decimal places. Then you got a 3 hanging out over here and a 1 hanging out over here. What you want to do is limit your answer to the fewest number of decimal places. In other words, imagine a line then. Let's see if I can draw that on there. This is not going to work probably. We'll see. It's not bad. Imagine a line kind of right there to where that's going to be your cutoff point. So whatever you have after this has to be rounded back to here, is what this is saying. So for example, if you line this up, you would get 9.214. Okay? That 4 is going to be past that line. That's your cutoff point. Okay? You have to get rid of that 4 and then round from that point. So when you do that, that's why that got kicked out to 9.21. So you might want to take note of that. But ultimately, just realize what you're going off of is not the total number of sig figs in this case, but the total number of decimal places present when you add and subtract. Okay. If you do this one and you line that one up, you'll see the same thing. Or if you don't need to line it up and you can do it in your head, that's perfectly fine too. Realize that you've got one decimal place, and that's all that you can do. Take that minus that, you'll get an answer on your calculator, 0.835. You've got to get that to one decimal place, regardless of what was in front of it. Okay, one decimal place, so that would be 0.8, 0.8. Yes? I guess I'm confused. Yeah, I'm not sure I understand what you're asking. These two examples just happen to be numbers that ended, well, no, I guess not.
It's in the problem. It's in the problem, whichever one number doesn't.
It's a good thing you understand what she said. Let's do some examples. Maybe it'll explain itself through some examples. Okay, well, if you understood that, good. Okay, let's mix it all up. We'll do some examples, and then maybe it'll work itself out if there's still any confusion. Now, what happens, because in real life, that's not the way it works, right? You don't just get a nice, happy math problem that's just addition and subtraction. When you get into this kind of stuff and you're calculating answers, you have to mix it all together. You'll have addition, you'll have multiplication, you got to work it all together. So how do you do that? Well, first of all, you follow the same order of operations as before. So if everything is just kind of strung across, first of all, anything in parentheses, just like in math, that's what you would do first. If there is no parentheses, you go through and you always do your multiplication and your division first and leave your addition and subtraction for later. This is just some basic math there. Okay. Let me show you how we're going to do this. Let's consider this problem. Here's the numbers that you have, 3.489, and you want to multiply that by the value of whatever this difference is right here, 5.67 minus 2.3. Okay, so what you got to do is you got to work in your parentheses. You've got to say, I'm going to get an answer for this, okay, and realize that what is going to limit, see if I can clarify it. I don't know if you can understand my question, but what is going to limit your answer here? Okay, thanks. 2.3. You got what I was saying. 2.3, that one decimal place right there. Okay? So what this is going to be is it's going to limit it. Now what you're going to want to do is just, whenever you perform this math operation right here, you don't want to just get your answer, chop it off right there and round it before you're all done with the problem. What you want to do is get an answer, and then you're going to keep underline where it is you're going to round in that number. I'll show you what I mean. You underline that and keep track of it in your head so that later on you can round off anything you need to. Well, I'll show you with an example. So you know, like you said, this is one decimal place. So you round, that would control it. Notice what I did there. See that? 3.37, but that 3 was underlined, because what I don't want to do is prematurely round all of this stuff before I need to. If I take 5.67 minus 2.3, I type that in my calculator, here's the answer that I get. Now, if I was finished, and that was all the math I needed to do, I would take that and change it to 3.4, and I would be done. But since I've got more math steps to do, I want to try to get the best answer that I can. Let's see if we can get you another chair here. I can't do much for space for you, but at least you can have a place to sit. That's all right. Okay, if I was done, I would take this to 3.4. My answer would be complete. However, I've got an additional step to do. So what I want to do is keep track mentally of where I would be, if I were done, where I would be done at in this number. So I would underline this 3 because that's the place where I would stop. Okay, that's why you see that underline there. So then I would multiply that by 3.489. Now knowing that ultimately I'll end up rounding this to two figures, right? And I've got how many sig figs over here? 4. So what's my answer of my product going to be limited to? How many? Right, 2. So what I will actually do, though, is type in this number in my calculator, okay, for a more precise answer, for something better. I'll go ahead and leave this number in my calculator, 3.37, realizing that in my head, that's actually where it had to have been cut off. Multiply that times this, and then I would get my final answer, whatever that final answer is at that point, now that I'm done with my math. Then I would go back and realize, okay, I had 4 sig figs here, only 2 here. My answer has to be limited to 2. Yeah.
So when you have addition, subtraction, and multiplication, division, your multiplication and division is always going to be last in this order operation. So you're always going to get an amount of...
Your multiplication and division won't necessarily always be last. If there's no parentheses, they're always going to be first.
Oh, yeah, that's what I meant. No way around.
Okay.
So since addition and subtraction will always be last, you'll go by your decimal point. That's the last thing you do.
Usually. I'm going to say usually, because I don't want to say for sure, because there could always be an example when that's not true. Okay.
When I did that out, it came to 11.75. So, instead of 1 decimal point 2,
Say again now.
instead of making it 11, why is it 11.8 and it's 12?
Because this only has 2 significant digits in it. You're actually doing a multiplication problem here. So you got to go back to multiplication division rules. This has 2, this has 4. That means your answer can only have 2. Because we're dealing with multiplication and division. That's this final step right here. Okay. All right. Now, getting into our units of measurement. As I mentioned before, I think I mentioned this in our last lecture, we are one of very few, one of I think maybe 3 in terms of economic significance, countries in the world who does not observe the metric system. However, you will have to be familiar with the metric system in this class and in any science class that you take, because that's the way the world works. We have SI units, stands for, what is it? I can't speak French. Système International, something like that, and then you could throw the accent on there. There are a certain set of units that are accepted as standards. For example, to measure length, the base unit to measure length in the scientific community is meter. Now, there's a lot of derivations of the meter, right? Millimeter, centimeter, kilometer, but functionally that suffix at the end is always meter. That's the base. Now, in terms of mass, you would think it would be gram, but it's actually defined as the kilogram. But certainly we have a gram, which is a 1,000th of a kilogram. We have a centigram, milligrams, right? All of these things. And so the kilogram is actually the base unit for mass. Is mass and weight the same thing? What's the difference? Okay, that's true. Why is weight not constant? It does. Weight depends on the force of gravity. Okay, weight is a force. It's not the amount of matter that you have. It's the amount of force you exert on something. So the amount of force that you exert on something is going to change depending on where you are in the universe. The bigger the object and the denser the object, the more gravity it's going to have, and thus the more pull down it's going to have on you, the more force you're going to exert on the surface. So you weigh less on the moon, 1/6 actually of what you weigh now on the moon. Yeah. Move to the moon, right? It may not be long, who knows? But mass, of course, is just how much matter is contained in something. So that's independent of gravity. Time is going to be measured from the base unit of second, and temperature, I'll talk about this later, in chemistry is measured in the base unit of Kelvin. Most of the time when you think of metric and you think of other countries, Europe, whatever, they use the centigrade scale or Celsius scale. We'll use Celsius in a lot of our calculations, but the SI unit for temperature is actually Kelvin. That becomes very important, and I'll explain why when we get into later chapters. But for now, just know that's what it is. Okay. This is what's very handy about the metric system and why we really need to go there, is because everything is by a factor of 10. It's real easy to do the math. It's whenever we throw in this ounces and cups and pounds things that we have that screws everything up. Everything is related to another thing by a factor of 10 in the metric system. And the power of 10 that you would increase or decrease that by is represented by the prefix, right? Like kilo means 1,000. Centa means 1/100th. Milli means 1/1000th. Mega means 1/1,000,000th, or sorry, a million times of what you have. So it's pretty easy. Once you know the prefixes, you can apply those to any of the base units that we've talked about. A centigram is 1/100th of a gram. A centiliter is 1/100th of a liter. So it remains constant like that. And there's what those are. You will have to be familiar with those. Okay, you need to have an idea. I'm not going to ask you directly, what does this word mean? It'll just be implied in the questions that you receive. So get a good idea. A lot of you probably already know these. If not, now's a good time to get to know them. Okay? So a deci anything, let's say a meter. A decimeter is 0.1 meter. In other words, that's a tenth, right? So that's 1/10 of a meter. A centimeter is 0.01 meter, meaning that's tens, that's hundreds, 1/100th of a meter. That's what these means. Speak good English. Now, notice that we've talked about scientific notation. So base times 10 to the minus 2. That's an easy way to do it because what you can keep in mind is times 10 to the minus 2 means 2 decimal places, right? So to convert back and forth between these things, it's really easy to do when you keep track of your decimal places. Like to go from a meter to a kilometer, or let's say a kilometer to a meter, either way, and depending on which direction you want to go, you just move the decimal place 3 places in either direction. Well, it depends on which one of those you're going to and coming from. So it's actually very simple to do. Notice that mega means 1,000,000 of something. So 1 times 10 to the 6th times whatever it is now. Okay, but since we are living in our country that we live in, and we do have to be able to deal with these conversions if we're going to work in the scientific community. So these are going to be very helpful. Now this is where you're going to want to go to the reference folder on the course webpage, print out that conversion sheet and keep it with you. Bring it to class, use it to do your homework problems, because there are a lot of useful conversions on there. Okay, you can certainly find those in a lot of other places. You don't have to just find it on my webpage. You can find conversion charts anywhere. In textbooks and little cards, they come all over the place. But here's some common ones. Okay, now this is very important because these are called conversion factors. These allow you to go from, let's say if I have a given unit of, say, kilometers, and I want to know how far that distance is in miles, for example. All I need to know is what is the relationship? How many miles are in a kilometer? Or how many kilometers are in a mile? Whatever, however you want to look at it. And if I know that, what I have is a ratio. I have a numerator and a denominator that are going to be expressing some sort of ratio. In other words, how much of a kilometer is equal to how much of a mile, or whatever. And if I know that, it's really easy to do the math and convert one unit to another. It's actually called dimensional analysis. Fancy way of saying converting things. Okay, here's some common mass conversions, some volume conversions. You realize, make sure you understand some vocab here. Mass is sort of like weight, but not really. It's just the amount of matter that something has. You can think of it as weight if it helps you, but realize there is a subtle difference between the two. Volume is how much space something takes up. So you need to be familiar with the types of units and what they measure. Mass is going to be like in grams. We can take pounds, which is weight. As long as we're on Earth, we can convert that to grams and kilograms. Volume is going to be like in liters or gallons. Think of especially the things that you would measure liquids in. Cups, liters, gallons, that kind of stuff. That's going to be volume measurements. That will change a little bit when we get to solids, and I'll show you that when we get there. Okay. If you give me a number without a unit, it's wrong, because I have no idea what that number means. So make sure you know that. Numbers have to go with units. Also, treat units like variables when it comes to math. For example, if you're multiplying, let's go back to some math here. How do you find the volume of a cube? Length times width times height. Let's say that the sides of the cube, all of them were on all sides 2 centimeters. Okay? That means the length was 2 centimeters, the width was 2 centimeters, and the height was 2 centimeters. How would you express the volume of that cube? Which is what? 2 times 2 is 4 times 2 is 8, right? 8 what? Cubic centimeters. That's my point. I want you to make sure you realize you treat these these units like you would a variable, okay, like an x or a y if you took algebra. When you multiply a centimeter value and a centimeter value together, you get square centimeters. If you multiply 3, you get cubic centimeters. That's the way it works. Because that's going to be important because you're going to have to start canceling stuff out and keeping track of all these units. So you got to get this stuff right. Okay, so like I said, this is all called dimensional analysis, what we're getting ready to start here. Some of you probably have already done this in other places. Some of you, this may be the first time you've seen this. So it's hard for me to know where everybody sits on this. So, okay, now, like I said, a conversion factor is going to be a relationship between two things. This is going to be immensely useful to you. You've got to know how to do this from the very beginning because it gets more complicated, I promise, as we go throughout the rest of the semester. Now, it may be exact or it may be measured. It may be a definition, like there's 16 ounces to a pound. That's a definition. There's 4 quarts to a gallon, by definition. Or it could be something that you've actually measured. There are, however many of your hands equal to 12 inches, whatever. It could be measured, it could be identified, it doesn't matter as long as there's a relationship that exists there. Okay. I want you to notice this bottom part right here. There are 2.54 centimeters in 1 inch, for example. Now what you need to realize is that if you're going to use that as a conversion factor for math, what that means is that either one of these is true. We're going to express this as a ratio. This equal sign actually means that for every one of these, there's 2.54 of those and vice versa. So we're going to put these together in fractional form and call it a ratio that we're going to use as a conversion factor. So what that means is, depending on what I'm starting with and where I'm going, as you will see in the examples, I can write that, I can express this equivalency either like this, 2.54 centimeters over 1 inch, or I can say 1 inch over 2.54 centimeters. It doesn't matter. Okay? Either way expresses the fact that they are related to one another. How you choose to write it depends upon what you're solving for. Okay? How are you going to set this stuff up? What you want to do is, like for example, if I say, here's your distance in kilometers. Tell me how far that is in miles. You're going to start with the original distance that I gave you. Then you're going to multiply by some conversion factor, some relationship between miles and kilometers. When you do that, you're going to get the answer. Now notice how this is set up. What you want to do is realize that, like in algebra, when you have variables above and below the fraction, whatever's on top and bottom can cancel out, right? If you have an x on top, x on bottom, mark them out. They'll cancel. Same thing will be here. Realize that this is the same thing as like over 1, right? So if you multiply these two things together, you would have unit 1 times unit 2 over unit 1, and then unit 1 would cancel out. That's what this is. Okay? I have a chair. Man, where all these people come from? Huh? I'm just taking them wherever I find them. I don't know. Somebody's going to come back to their office and not have a place to sit. I don't have a table for you. Sorry. You have to squeeze in. Get cozy with somebody. But if you set it up like this, what you will see is that the units will cancel out. Okay? The units you're trying to get rid of will get rid of themselves, and the units that you have left are the ones that you want to get to. So that's the way this will work. Let me put some numbers in here and try to make some sense of this. Okay? Now what you will see as we go along, when you get good at this, we're going to be able to string this out. We may be able to put like 6 steps in here, and everything will cancel out as we go, and we'll end up with the answer that we want in the very end. But we'll get there. Okay? All right, so let's take this example. If I ask you this, convert 7.8 kilometers to miles, how can you do that? Now I know that like in your head, you could probably do this. Or at least like if I said 3 dozen donuts, how many donuts is that? Or 36, right? You can do that in your head. I don't want you to. And the reason is not just to be difficult. The reason is because I'm preparing you for a future chapter, in which case you will not be able to do these things in your head. Get the method down now while the problems are easier. Okay? All right, so 7.8 kilometers. I want you to convert that into miles. So here's what you're given. Here's what you're trying to find. What do you know? Is there a relationship that is known between kilometers and miles? Well, this is where a conversion sheet would be very handy. You would look it up and you would find a relationship there. In this case, this is known. There is 0.6214 miles in 1 kilometer. Okay? So, where are you coming from? What unit are you leaving, and what unit are you trying to get to? You are leaving kilometers and trying to get to miles. So the question then becomes, how do you arrange, how do you position your units so that they will cancel out properly and you will be left with the unit that you want in your final answer? Well, this makes sense if you look at it like this, right? If you know that this, whatever ratio this is right here, it has to be this equivalency, this conversion factor. So put it here. If I put miles on bottom, will they cancel out? No. I want to get rid of kilometers and I want to be left with miles. So I'm going to have to put kilometers on the bottom. They will cancel out. And then whatever number I start with, it'll end up being 7.8. When I start multiplying that together, the unit that I'm left with is going to be miles, and that's what I want in my final answer. Okay, so look at the solution. I start with what I know. I'm 7.8. What can I multiply that by in order to get to miles? Well, I know that this many miles are in this many kilometers. Okay, so these will then cancel out. And notice that when I multiply these numbers together, I'm going to be left with the unit that I want, miles. That's the way this is going to work. Now, what about significant figures? This is actually a measurement. See all those decimal numbers there. Okay. Now, 1 kilometer, well, actually, since this is a conversion factor that you look up on a sheet, we're going to say that anything that you look up on the sheet like this, that is a defined conversion factor, it is not going to have an impact on the number of significant figures that you have in your answer because it's not something that you measured. See what I mean? It's not something that was limited by the instrumentation that you were using. Therefore, you can just use it for what it is. And what you're going to be limited by would be this 7.8 because that is a measured distance. That's not a definition. Now, you may not have personally measured it, but you're given that quantity, and that had to have been a measured quantity because there's an infinite possibility of the number of kilometers that exist, right? So you're given 7.8. That was some measured quantity by somebody. That's what's going to limit your significant figures. This is a definition. This is a conversion factor that you are using. Okay? That will not limit it. So, in other words, you are limited to, this is a perfect number, so that's not going to affect your significant digits. Here you've got 2 sig figs that you need to worry about. So you would take this long number, and it's a multiplication, so you're limited to the least number of significant figures that are present, which in this case is 2. So you would take that number to make it 4.8 miles. Okay? So the answer is, how many miles are in 7.8 kilometers? 4.8 miles. Follow me? Okay. Spice it up a little. Okay. Literally, I guess. We're making some Italian food. Let's consider this problem. An Italian recipe for making creamy pasta sauce calls for 0.75 liters of cream. Your measuring cup measures only in cups. How many cups should you use? Okay. You've got your Aunt Sophia over in the motherland, and she sends you this recipe because that's the way they measure things over there. But she doesn't translate for you. She's not been skilled in the art of dimensional analysis. You, on the other hand, have. So you can make this conversion. All right, how are we going to do this? We're going to have to find a relationship between liters and cups. Now, you could look on your conversion sheet, and you could look in a lot of places, and there may be a place listed somewhere that has an equivalency between cups and liters. There certainly could be. But there doesn't need to be, right? There's a lot of different ways to solve this problem. All you've got to do is keep track of where you're going and cancel out units properly, and as long as you're left with cups in the end, you're going to get the same answer as if you did it in 1 step or 6 steps. It doesn't matter. You understand why? You get that. If you string all this stuff up, you can take the long way around, or you can take a shortcut if you've got something that tells you exactly how many cups and liters, what the equivalency is. If not, it doesn't matter. You could go from liters to milliliters, milliliters to pints, pints to quarts, quarts to gallons, gallons to deciliters, deciliters to fluid ounces, and then fluid ounces to cups, if you wanted to. That's a ridiculous way to do it, but you could certainly do that, and you would end up with the same answer as if I did it in 1 step. So realize there's no right or wrong way, as long as you keep track of your units and they cancel out properly. Okay? All right, here's what we do know. 0.75 liters. You've got to convert that to cups. How do we do it? Well, here's what we know. at least according to this problem. Maybe it's on your sheet different, but I'm going off this. Okay? 4 cups, that's 1 quart. And 1.057 quarts is 1 liter. Now, can I use that information? I'm going from liters to cups. If I go from liters, I can use this to go from liters to quarts. Once I'm at quarts, I can go from quarts to cups. So there you go. Now, I know this is kind of kitchen kind of stuff. You may not see the relationship to chemistry, but let's just hold off on that because it'll hit you hard enough and soon enough. Okay, so just stay with me here on the procedure. So we're going from liters, like you said, to quarts, from quarts to cups. Now, how do we go from liters to quarts? We're going to use that conversion factor right there. The 1.057 quarts equal to 1 liter. Now we got to figure out how we want to position this so that things cancel out properly. We're going to want to put the liter on the bottom, right? To get rid of that. The quarts on the top. Now I want to go from, if I stopped my answer right now, my answer would be in quarts if I stop. I don't want to stop. I want to go from quarts to cups. I'm going to need another conversion factor to do that. So I want to put quarts on bottom so that this cancels out, which would be over here now, right? This cancels out. I'll be left with cups. So then I plug in my numbers. 0.75 times 1.057 over 1 times 4 over 1. When I do that, cancel, cancel. My answer's in cups. I would get that answer right there. I am limited to, remember these are my conversion factors, right? Over here, how many sig figs are there? There's 2. My answer has to be rounded to 2, 3.2 cups. Okay? Questions about that? You know everything? We'll see. Okay. Now, probably the most important step out of all this, common sense. As Eleanor Roosevelt once said, common sense isn't so common. Right? But think about this before you slap this down as your final answer. Does it logically make sense what is going on? Which is probably bigger, liters or cups? I mean, common sense tells us liters are bigger than cups. So if I have a very small liter value, since cups are smaller than liters, it's going to take more cups to equal that, right? So just make sure that your answer makes sense. In this case, you've got more cups than you do this value here. That makes logical sense. You can't always predict what the number is going to be, but you could certainly decide if that was like 0.32, you know that that's screwed up. It can't be right. It just doesn't make sense. So employ a little common sense to these problems as you're working through them. Okay. Now, anybody ever pour concrete in here? One of the tough, if you order concrete, I don't know if you've, I was poor when we built our first house, so I had to do this stuff myself. But one of the things that's kind of hard to do is to guess up, how much concrete you want to order, right? Because you can't take it back, and they don't take it back. You pay for whatever they put on the truck. How do they sell it? By the yard or square yard is the way that they sell concrete. Now, how do you, if you're taking a floor and you want to make a concrete floor, you can certainly calculate the volume of that floor. If you know it wants to be 4.5 inches thick, and you know the dimensions, right, how big it is, you can calculate base length times width times height, like we did a while ago. You can calculate that volume. Now, what's tricky is you measure things probably in feet. Let's say you measure that in feet. How do you convert that? How do you convert like cubic feet, for example, to cubic yards or meters? Cubic meters to cubic yards. When you get into those exponents like that, changes some things. You got to consider something whenever you do these conversions. It's not too bad. It's not hard. But let's just consider this, for example. A circle has an area of 2659 square centimeters. What is the area in square meters? Okay, you would think you automatically want to realize that that's probably 1/100th of a meter. That makes sense, and you're right. However, you got to keep in mind that we're dealing with square centimeters here. So how does that impact canceling out of units? Well, if you write it out like I've showed you to write it out, and not do it in your head, you'll see exactly what I'm talking about. You want to go to meter squared. Here's what you do know. You do know that 1 centimeter is 1/100th of a meter. Now, another way you could write that is there are 100 centimeters equals 1 meter. It's the same thing. Doesn't matter which one of those you pick. Either one will work. So let's use this conversion factor. We're going from square centimeters to square meters. How am I going to do that? That's how. Keep in mind, I had to have that exponent there. Yes, I got to have this on bottom and that on top for this to cancel out. But if I just had 0.01 meter, and this was not there, 0.01 meter over 1 centimeter, notice that only one of those centimeters would cancel out. I'd still be left with the centimeter. I've got to have it squared, otherwise it won't cancel everything out. So what ends up happening is it's not just a straight 1/100th of a conversion, because you end up squaring this value right here. Okay? So what you end up with is this. Because 1 times 0.01, realize what that is. That's 1 times 10 to the minus 2. What's 1 times 10 to the minus 2 times 1 times 10 to the minus 2? It's 1 times 10 to the minus 4. Okay? That's where this number came from right there. So you've got 1 times 10 to the minus 4 square meters over 1 square centimeter. Now these will cancel, and your answer will be in square meters. So just don't forget, if you have to do any exponential type of conversions, keep this in mind right here. You'll have to raise everything in the whole conversion to the power that's necessary to cancel out. That means you have to include that number as well. Questions? Now we got a sig fig and round it here. So we've got 1, 2, 3, 4. I've given you 4 up here as your problem. This was a definition, so that doesn't impact us. We've got 4 sig figs here, so we can go to 4. So that's why this answer is in 4 significant figures. Get in the habit of doing it. Yeah, I may give you a little slack in terms of what happens in lecture, but I definitely will count off for it in lab. So you might as well just get used to it, and that way you don't have to. Okay, one of the last topics here, density. This will be useful. This will be our second lab that we do. We'll be doing a density analysis. It's pretty straightforward. Density. What density is a ratio of the mass of something to the amount of volume that it occupies. And what that means to you is it's important in identifying something. For example, the density of the density of liquid water at 4 degrees Celsius. Okay? The density of water means that if I have 1 gram of water and I put it on a scale, if I have 1 milliliter of water, I measure it out, 1 mil, put it on a scale and weigh it, it's going to weigh 1 gram. That's what water is. Water has a density of 1. What that means is the ratio, in other words, the fraction, if you put the mass on top and the volume on bottom of any situation, it will remain constant. For example, if I have 1 milliliter of water, I put it on a scale, it's going to weigh 1 gram. If I have 2 milliliters of water and I put it on a scale, guess how much it's going to weigh? 2 grams. If I have 100 milliliters of water, it's going to weigh 100 grams. Every time I take the gram value and divide it by the milliliter value, I get the same number. That's the density of water. That's the ratio of its mass to its volume, always. And you will find that all these things out there have their own unique density. It's sort of like their own little fingerprint. There's a whole lot more in terms of fingerprinting things, and I'll talk about that, especially when we get into electrons and atoms. It'll blow your mind. Okay? So let's consider this. Mass and volume themselves are the 2 main characteristics of matter. Okay? Consider this. I can't necessarily use it to determine what type of matter something is, but it can certainly describe the situation in which I find myself in terms of how this seems to be behaving. It'll lead to help us identify something. For example, if you are given a large glass containing 100 grams of a clear, colorless liquid, and a small glass containing 25 grams of a clear, colorless liquid, are both liquids the same stuff? Well, you don't know by looking. There certainly are a lot of chemical tests that we could do, but what's something very simple that we can do? We can take a given mass of it, take a given volume of it, and then weigh it, or mass it, I guess, on a scale, and see what the ratio is. Do the same thing for the other substance and see if that ratio is the same. It shouldn't matter what volume I pick, because what you'll see is the weight will increase proportionally to the volume that I put on there. So this is one way to see if 2 things are the same, made of the same material, for example. You'll see a Greek philosopher came up with, Archimedes actually, but came up with a really interesting scenario for a king a couple thousand years ago. I'll talk about it here in a second. So the mass and the volume are certainly related to each other. Okay. By the way, if you ever wonder how these giant aircraft carriers, right? These ginormous ships that are out there, how in the world do they stay above water? Because you know that if you took a steel ball that only weighed, I don't know, a fraction of a pound, and I dropped it in water, it's going to sink straight to the bottom, right? Why can I take these massively huge ships, put them on water, and why in the world do they float? You ever really think about that? Surface tension and buoyancy certainly have a lot to do with it. It has to do with playing with this ratio of mass and volume. Okay, the bigger you make this boat, the more you spread it out, what you do is you increase its volume, right? By having, I could take all the metal that was in one of these boats and I could compress it all down and make this dense like cube or ball. I drop that in the ocean, it's going straight down. But if I spread it all out and I pull this metal out and make it take up a bigger area, you know that density is mass over volume. I'll show you this equation in a second. It's mass divided by volume. The mass hasn't changed, whether or not it's this big or whether it's as big as this room. The mass is going to be the same. It's the same amount of matter that's present. What have you done? You have changed the total, the volume that mass occupies is what you've done. You spread it all out. So what does that do to the ratio? That denominator, what happens to it? Right? That denominator gets bigger and bigger and bigger. What happens when a denominator gets bigger? Does the number get bigger or smaller? It gets smaller, right? The smaller it gets, that's the goal. Because when you mix two things together, whichever one is more dense than the other is going to stay underneath. Whichever one is less dense is going to float on top of the other substance. So you can create something like a large ship, for example, manipulate its volume that it takes up, so that when you divide the mass by the volume, you actually get a number that could be less than the density of water, let's say. That's not completely true, but for my point of illustration, you get the concept. Okay, there's some other things I would have to explain in terms of physics for that, but you can see how you can manipulate that to a benefit. It's sort of a, you ever notice too, anybody ever go to a family reunion? And you know, down where I'm from, that's what you do. You go to family reunions, and it's the same crap every year. You know, the same people bring the same thing and set in the same places. Potato salad, big tub of pop. Next time you're at this big tub of pop, if you got a big one and it's good and cold with ice water, not a whole lot of ice in there, but it's just good and cold with the cold water now. Look and see, especially if there's not a whole lot of stuff in there. Compare in this giant tub where the diet pop is versus where the regular pop is. Diet pop is actually a little bit less dense than water. It will float in water. Regular pop will sink in water. There's a little bit of a density difference between the two. Now, it's not completely obvious. What you can do is if you go slow, like if I do a demonstration for one of the lab videos that I made here. If I have two big containers and I let go of them very easily at the same time, the regular Coke will sink straight to the bottom. The diet pop will just sort of float right underneath the surface. Not all the way at the top, but right near the surface. You can start seeing this if you pay attention. These are just some things that you might pick up on. All right. So here's an example, an illustration. Let's say we have brass. Brass is an alloy made of zinc and copper. Okay? We'll talk about those type of things later in the semester. But if I have certain samples of brass, and let's say they're cubes, because cubic centimeters, that way they're easy to measure. I can calculate the volume very easily. Say I have different cubes of brass. And I have a 2.4 cubic centimeter size of a block. I mass it. It weighs 20 grams. I get a bigger hunk of this same sample of brass, and it's compress it into a 3.8 cubic centimeter block. I find that it weighs 32 grams, and so on and so forth. Okay? Notice what is happening. I'm increasing the volume. Notice what else is happening. The mass naturally increases the more of it that I have. My point is, what I want you to see with density is that there is a number that is constant. It increases by the same factor every single time. Because what happens is if you plot that, you should have made graphs before. If you take, like in this case, notice the volume here at the bottom on your x-axis and mass on your y-axis. So if you use these numbers, you put this along your x-axis, put this up your y-axis, and meet the points and make a line graph, or just connect the dots, and then with a line it ends up being a straight line. what you will see is that it forms a really nice line. It's a linear proportion. Whenever the volume goes up, so does the mass. And they happen to go up in a very linear fashion by the same, to the same degree every single time, the same relationship. So as if you took this number, whatever this mass was at this point right here, and divided it by the volume, and you did the same thing here and the same thing here, you would constantly get the same answer over and over and over. That's the density of that object. So, D is equal to m over v. Density is mass divided by volume. You'll need to know that. The way that we express this in terms of solids is to use cubic centimeters. Because milliliters, you usually use that for liquids, right? It's not very handy in terms of when we're dealing with solid material. So one way to measure volume is like length times width times height, which would be like a distance measurement, like centimeters, meters, whatever. So one way that you measure solids is grams per cubic centimeter. Like I did with that brass thing. You can measure the volume in cubic centimeters, put it on a balance, get a gram value. Now, one thing you might want to know, depending on what field you work in and what things you've heard and what TV shows you've watched. 1 cubic centimeter, that's what a cc stands for. Okay? 1 cc is 1 cubic centimeter. Now, also, when we're dealing with most liquids, you can assume that from here on out, but it's not always true, but we'll assume it for now. We're going to say that 1 cubic centimeter is equal to 1 cc because they're the same thing, but that is the same as a milliliter as well. So if I have 30 cc's of water, I have 30 milliliters of water. Okay? So those two are interchangeable. Make sure you know that. Now when we measure density, remember I said what density was. It's mass divided by volume. So here's a mass unit. There's a volume unit. Here's a mass unit. Here's a volume unit. Here's a mass. Here's a volume. Notice that depending on the state of the matter, whether it's a solid, liquid, or a gas, we may use different units. You should recognize that, though, if you see this like this, some sort of mass in proportion to some sort of volume measurement, we're dealing with the density value there. Okay? You would use liters, for example, for gases because gases occupy so much more space. They spread out a lot more, so it's harder to limit them. You get a much fewer number of particles when you use small measurements. Okay? Now, what if you have something that is not easily measured? For example, a rock, or a ring, or a penny even, because pennies get worn over time, right? What if it's something you can't measure very well, but you need to calculate its density? Well, there was a guy named Archimedes, who was a Greek scientist, Greek philosopher, who was sitting. You ever heard the expression eureka, right? That this is a guy who's attributed to. I found it, right? Eureka. He was sitting in the tub. A lot of great discoveries have happened in the bathtub, by the way. I'm waiting for my epiphany. It hasn't happened yet. But there's a guy named, what's his name? The guy on the atomic bomb. Salt somebody. He gave that letter to Einstein. Einstein had to sign for FDR. Anyways, that guy was crazy. He was like a physicist and theoretical scientist who would take these like long, hot baths for like hours at a time and spend all morning in it, and that's how he would think. That was how he came up with all of his ideas. Ultimately, it led to all the research that went into the making of the atomic bomb for our country. But anyways, Archimedes was sitting in his bathtub, and what he realized was when he sat down, what happens to the water? Yeah, it displaces, right? Now, you might think, ooh, this guy's a genius. You know, he figured that out. But guess what? He was the first guy to write it down and to share it with other people and come up with an explanation how it can be used, so therefore he gets credit for it. That's the way the world works, right? So we call it Archimedes' principle, this principle of displacement. And what he basically came up with, it wasn't just that. He just didn't say, ooh, look, the water went up. He came up with some sort of mathematical relationship to say, you know what? The amount of water that went up was the same amount of volume that I occupy. So he's saying, I moved that water out of the way. However much volume comprises me is how much water I pushed out of the way. So if I have an irregularly shaped object, like a rock that you can't really measure, and I drop it into water and I see how much water is displaced, I take the difference between where the water line was, where the water is now, if it's in milliliters, for example, and now I have a milliliter measurement for that object in terms of what volume it would occupy. That makes sense. Okay, one thing to keep in mind. Solids have a much, much greater density than liquids. Okay? For any given volume of a solid, there's a lot more matter packed in. That makes sense, so it's a higher density. Liquids have a much higher density even than gases. Gases are very, very, very low density. We'll talk about gases in a whole chapter later on. Now, except ice, and this is interesting. We'll get to this too later on. Why is water so special? Why is water so important to life? There may be things you haven't thought about, but water. I'll just throw this out for now. Water is the only chemical on this planet that naturally exists in all three states of matter: solid, liquid, and gas. No other chemical does that on this planet. Not only that, water is the only chemical in which its solid phase is less dense than its liquid phase. Liquid water doesn't float on top of ice, right? Ice floats on top of liquid water. It's less dense. It's the only compound where that happens. So those two things should be enough to think about. We'll discuss them further as we go along. Okay, so be able to manipulate these equations algebraically. So if I want to solve for density, I know I take the mass divided by the volume. What if I wanted to solve for the volume? I would take mass. You'd have to bring this up here, then bring density down here, mass divided by density. If I wanted to solve for mass, I would have density times volume. You've got to be able to do that. Okay, so read that for a second. This is how you can bust somebody. Okay? Man gave a woman an engagement ring. Tells her that it's made of platinum. Noting that the ring felt a little light, because obviously a jewelry connoisseur, she would know this kind of thing. The woman decides to perform a simple test to determine the ring's density before giving him an answer about marriage. Are they off on the wrong foot? Is he lying to her already? Jerry. She places the ring on a balance, because that's what you have at home. Everybody has a digital balance at home. She places the ring on a balance and finds it has a mass of 5.84 grams. Okay? Now you could probably use a kitchen scale, like do ounces, and you can convert ounces to grams if you wanted to do this. She then finds that the ring displaces 0.556 cubic centimeters of water, because you all have graduated cylinders at home too. I actually do. It's right above my sink to the right with some other things. Got a graduated cylinder and a beaker up there. I'm not sure. I think I brought it home for my daughter for some reason. All right, so you realize through unit conversion, there's a lot of ways you could come up with this. You could measure in different units depending on the stuff that you had, and you can convert either way. Grams per cubic centimeter is where you'd probably want to get to. This is a common expression for solid objects. It's common units to use for density. So she would weigh it, and she would then take it and drop it in some water and see how much the water level changed in milliliters or cubic centimeters. Remember I said those two things are the same. So if you measure 0.556 milliliters, that's the same as 0.556 cubic centimeters. All right, so is the ring made of platinum? Well, fortunately for her, unfortunately for the guy, there is a table listed in about every chemistry textbook that exists on the planet that has a lot of the common densities for a lot of the most commonly considered metals. This is measured over and over through the generations and through the centuries, so this is common knowledge. You would look it up, and you could see that the experimentally determined density of platinum by everybody is about 21.4 grams per cubic centimeter. Now the question is it made of platinum? Let's see. There's what you know. That's how much it weighs. That's how much volume it occupies. You can use the relationship between the mass and the volume. That's what density is. So regardless of how big this platinum chunk is, it doesn't matter, because the volume is going to change accordingly with the mass. So divide them, see what number you get, and see if you get that 21.4. Will you in this case? It looks like probably not, but let's see. Density is going to be mass divided by volume. So you've got the mass, got the volume. Divide those two. What do you get? You get 10.5 grams per cubic centimeters. Definitely not. Okay. Now if it was close, maybe you could warrant further investigation, but that's half the value of what it should be. That's not close enough. Okay. So in that case, that ring cannot be platinum. Now, using density as a conversion factor. Because remember, it is a relationship between mass and volume. So since you have that numerator-denominator relationship and you can flip them, that still is an equivalency. That is a conversion factor that you can use. Let's look at an example. For example, if you look at the density of water, I told you that for every 1 milliliter of it you had, it would weigh 1 gram. So 1 gram per milliliter. 1 divided by 1 is 1. Therefore, that's what that means, right? Therefore, 1 gram of water is equal to 1 milliliter of water. That's a conversion factor. Lead. Lead has a density of 11.3 grams per cubic centimeter.